Okay, we've got something interesting here. Today what I want to do is derive the formula for the Digamma function for half and integer values. So like something in the form k plus 1/2, where k is going to be a positive integer. And to start with, we're just going to use our series expansion over here to the right for the Digamma function, where we've got something, we have it in terms of a series minus the Euler-Mascheroni constant, which is something like 0.577. So what I'm going to do is, basically what I'm going to do is just going to plug that in for our z value right there. So we're looking for Digamma of k plus 1/2 using this formula. We're going to have minus Euler-Mascheroni constant, the sum 1 over n plus 1, plug that in for z, and we're going to have minus 1 over n plus k plus 1/2. And then let's just work on this sum right here and simplifying this part. So what I can do is, I think what I want to do for my first step is I don't really like having half there. Let's multiply into this thing everywhere 2 over 2, so we're just multiplying by 1. So when we do that and rewrite, this one here, we'll leave a 2 out front, and then this is going to become 1 over 2n plus 2 now. And then for the second piece, this is going to become 2n plus 2k plus 1. And what I'm trying to do is I'm trying to pull like the alternating harmonic series out of here. So I need to create some other terms. What I want to do on this one here, if I just subtract in, I can subtract in here minus 1 over 2n plus 1, but I don't want to change it again. So I'll add in 1 over 2n plus 1. That way we're just adding 0 here. And then doing this, let me rewrite and break it all up. We're going to break this now into two sums, I think. So let's see how that looks. And then one more thing here, let's reverse the sign on it. So if I just change the sign here, like multiplying in minus 1, don't want to change it, multiply by minus sign out front. And then just for this right here, let's expand it out. So let's just look at some terms. So you plug in 0, you get 1. The second term, you get minus 1/2. Then we plug in n equals 1, we're going to have 1 over 3. And what's happening here, this is going to be our alternating harmonic series. And this has a known value, so we'll just use that. This here is going to be just natural log of 2. So now let me try to just stay organized. I'm kind of a little bit all over the place in this one, but we want to capture everything we have. So we have, in our formula, we're going to have minus Euler-Mascheroni constant here. This is going to become minus 2 ln2. Get rid of this stuff. And then we're going to have this, let's just say plus this sum here. And that is, when I say this sum, we still need to find a value for this thing. So let's focus on this and see if we can finish off our formula. Now for what we have left here, again, let's expand out some terms and just see what we're looking at. So if you plug 0 in for this first one, this is going to be, let's write it like 1 over 1. Then we're going to have, that's going to zero out this, is going to become 1 over 2k plus 1. Then for the next term here, this is going to become, plugging in n equals 1, this is going to become 1 over 3 plus 1 over 2 plus 2k plus 1. Then we'll do another one. You plug in 2, this is going to be 1 over 5. And then this is going to be 1 over 4 plus 2k plus 1. And this, of course, is just going to keep going like this, on and on to infinity. But the thing to notice here, now notice everything here, this is pretty simple on these alternating terms where we just have an odd denominator. And the other thing to notice is this here, this is also going to be an odd integer in each case, just because we have 2k plus 1 in it, and the first part's even. So this part's always odd. So what's going to happen is this is actually going to telescope eventually. And so what we can do is kind of sum this whole thing up. So we've got our 2 out front. I can write this sum as n equals 0. And then our last term on this is actually going to be k minus 1. And we can write this as 1 over 2n plus 1 in order that we're getting an odd number in the denominator here. And this way, this is set up where all of these alternating terms are going to cancel with something. And we just get our last term is going to be this k minus 1 term. And then one last thing I can do on this, we can do an index change on it. If I actually, like if we want to add one here, that way I can add one here and then just subtract one right here. So let's see what we have. This is going to become 2 times the sum n equals 1 to just k now. If we subtract 1 on here, plugging minus 1, if we subtract 1 in here, this is going to become like 2n minus 2 plus 1. So now we have this as 2n minus 1 with the 1 in the numerator. And let's just take that and we can plug that into our formula up here. And now this is one way to do it, but let's clean up the board and we can look at a second way that I think might be a little bit easier or a little more straightforward, but let's see how it goes. Okay, so for the second method on this, I just want to use this recursion formula over here to the right. And so because k is a positive integer, and each time we perform this, we're reducing the input by 1, then eventually k is going to eventually be 0, and then we're going to have gamma of 1/2. But for that value, I derived that in a previous video, and so we'll just use the value for that. We'll have to go through all the steps, but eventually we'll get to this value that we know, and let's just capture that over here. So then going ahead with this, we'll just use this formula. So we start with our gamma of k plus 1/2. But I think I want to write it a little bit differently. If I just multiply in 2 over 2 here, we can put this together and write this as 2k plus 1 over 2 on this. And then applying the formula, subtracting 1 odd to get here, we end up with digamma of 2k minus 1 over 2 plus the reciprocal of this, which is just going to be 2 over 2k minus 1. And then we'll just perform the same exact thing a few more times just to see where it's going. So like doing it again, this is going to reduce this one, which is this right here. It's going to reduce this one to 2k minus 3 over 2 plus this reciprocal. Let's just do it one more time on this thing. And of course we could do this forever because we don't know how big our k is, but let's just say eventually we're going to get to digamma of 3/2. And so using the formula on digamma of 3/2, this is going to be digamma 1/2 plus the reciprocal of 1/2, which is just 2. So then what's going to happen is when we try to put all this stuff back together, see we're recursively plugging back in, so all these terms here are going to go away. This one is going to be left, but we captured that here. We know this value right here. This is this. And then we need to sum up all these values here. But you'll notice, again, we've got this odd integer value in the denominator here. And so like this first term, we can look at this as 2 over 1. And then the second one, we can look at as 2 over 3. It's kind of easier going from this way up. And then for this one, it's going to be 2 over 5. And then eventually we're going to get all the way to 2k minus 1. So if we take all this and try to sum it up, what's going to happen is we end up with, we can write this as, to get an odd value here, I can write this as 2n minus 1 in the denominator. That's always going to be an odd integer. Starting at 1, that way our first denominator is going to be 1. You plug in a 2, you get the 3. So that works. And then for this upper value, this here is actually going to be k. The reason why it works in this case is if you mess with this and you count how many rows we have, how many terms we're going to have, it's actually going to be k. So this way we get k terms. Everything with this should be a 2 in the denominator the way we have it here, the way we have it written out. So it'd be like 2 over this 2n minus 1, which always gives an odd denominator. If I take this 2 out front, then it's going to match our formula. We'll have 2 times the sum from n equals 1 to k of 2 over 2n minus 1. This piece matches this part of the formula right here. And then everything else, this stuff right here, this is just our digamma of 1/2 value that we have right here. And so this is just another way to get the same formula using the recursive method. Anyway, so there you have it. That's it for today. Thanks everyone for watching. Have a good day.